Hello and welcome to this video. In this video we're going to be looking at gravitational field strength and also gravitational potentials. So there's a reason I've brought these two together in this video, is because they are very closely related. But there are some distinct differences between the two. So what I'm going to do in this video is we're first going to define what is field strength, define what a potential is, and then look at how we can solve for those and what the differences and similarities between those are. So let's start with field strength. What we've looked at so far in gravitational fields is the force, right? So we said that we can state Newton's law of gravitation, which is F is equal to gmm over r squared. And we said that we make approximations when we do this. We can say that we approximate this to be a point mass, but we can also say we approximate this field to be uniform, and we said we can do that based on our perspective, because it doesn't matter where we stand. According to Einstein, the laws of physics should always remain the same, which makes sense. So it means that just because we have a different equation for force doesn't mean we can neglect the other equations for force due to gravity that we already know. And at the surface of the Earth, we know that the weight force is actually just the mass times the gravitational acceleration. But this, now we're going to stop calling the gravitational acceleration, because this is actually the gravitational field strength. Okay, so this means that if we now have two equations that are both equal to F, I can do a number of things. I can first say that I can just work with this equation, and I can define gravitational field strength to be G is F divided by M. Okay? And this is your first equation that you'll see of gravitational field strength on your formula sheet. And it allows us to formulate the first part of a definition. We can say that the gravitational field strength is the force per unit mass. Okay? But this isn't our full definition, because we have this second equation and we need to combine these in some way to get a full definition of what this is. Because right now we know F is actually equal to gmm over r squared. So if I go over here and I say that if these are both the force due to gravity, I can say that mg is actually equal to gmm over r squared, and I can cancel out an m. This is the same as doing this force divided by the mass. I could cancel out this m here, and it leaves me with the equation that G is also equal to gm over r squared, which is the second equation. Now the reason this is then going to help us to formulate the rest of this definition is because it's based on r. Okay, we're saying that if we just define it as the force per unit mass, we are basically trying to say that the gravitational field strength is the same everywhere. This isn't true. We know the further you go away, your force is going to decrease. We looked at that in the gravitational force video. So it means that actually, if from this equation the force is directly proportional to the gravitational field strength, it must mean that as the force decreases, the gravitational field strength would also decrease, which means at different points in the field you have a different value of the gravitational field strength. So the rest of our definition is this is the force per unit mass felt by a test mass at a point in the field. Okay? So we're saying that the field strength, our definition of field strength currently, is we pick a point in the field and we say what force per unit mass would a mass feel, right? We don't have to specify what mass that has, but we've usually just take the example that it's just a small mass, we put it there, what kind of force is it going to feel? And we know that as we move it closer to a planet or closer to a star, the force is going to increase, because force is directly proportional to the gravitational field strength. The gravitational field strength must also increase. But how do we visualize that? How do we get our heads around what that visually means? Okay, and to do that we need to look at the field lines, because the field lines will actually tell you a lot about the gravitational field strength. So what we're going to say is, we can say that we could know from logic, I guess, that the gravitational field strength on Earth is going to be very different to that on Jupiter. On Jupiter, you have a much bigger mass, which means you're going to have a much bigger gravitational field strength. And so what we can say from there is, if we were to take an approximation of a uniform field on both Jupiter and Earth and see what they both look like, we can say that if we set Earth to be, it looks something like this, then it means Jupiter is going to look something more like this. Okay, so the density of field lines is proportional to the field strength. Proportional to the field strength. Okay, so if you have a larger mass, you will get a larger field strength for the same radius. Okay, we've kind of briefly made the assumption that Jupiter and Earth have the same radius. It's obviously not true, but it's still a valid approximation, since the change in the radius isn't going to affect the gravitational field strength difference too much. So this is basically our whole idea of field strength. Now, the last thing that we should note is that it is a vector. Okay, gravitational field strength is a vector quantity. Okay, it's a vector because we know it's the force per unit mass, and force is a vector. So if it's directly proportional to a force, and the constant of proportionality is m here, so if we were to write this out properly, the force is directly proportional to the gravitational acceleration or gravitational field strength, where m is the scalar. Now, in general, if you multiply a scalar by a vector, you end up with a vector. Okay, so that means if I take a vector and I divide it by a scalar, I end up with a vector. So this f is my vector divided by a scalar, g must be a vector, and it points in the same direction as the force. So in same direction as the force due to gravity. Okay, now from here we need to then look at potentials. So this is our definition of, if we take this field at any point in that field, we can quantify its gravitational field strength there. But we can also have another quantity which is called the potential. So now if we scroll down and look at potentials, now in order to derive what a potential is, it's a little more complicated. You need a lot more maths knowledge. What I will tell you in general, so for anyone doing maths, so I'm going to put this in a box up here, just to separate it. If you're not going to need this for your exams or anything, but in general, for anyone interested, the potential is just the derivative of the field strength with respect to distance. So with respect to r. Okay. Now, those of you who are doing maths could probably prove that. But I'm just going to quote that if I were to take the differential of the electric or gravitational field strength in this case, then I end up with a potential which we note as a V, and that's going to be equal to minus Gm over R. Okay. Okay, so this is your equation that defines what a potential is. Now, in order to put this into a definition, it's not as straightforward as we did with the electric field strength, because your potential is actually, when we've heard the words potential before, they've always either been in mechanics AS, where we've looked at potential energy, gravitational potential energy, or they've been in electricity, where again the potential was a measure of the energy per unit charge. Now, this is going to be something very similar. So in this case, our potential, our definition of potential, what it actually is the work done per unit mass to move a positive, or actually let's just go with test mass, to move a test mass from infinity to that point. Okay, so we're saying it's defined by the position that you are in the field. And we know that because this is based on R. Now, there's a kind of trick with this, I guess. And the trick is that why is this negative? Why would we have a field where we're going to end up with a negative potential and then end up with negative potential energy? Okay. Now the reason for this is because we set a potential based on how much energy we'd have to put in to get outside of the gravitational field. Now if I imagine, so this is the question, why is it negative? Because it's negative in every point of the field, so surely this has to have a good reason. And the reason is, if I were to take, let's say this is my point mass of whatever it is, and then this is the edge of its gravitational field. This is an infinite distance away, okay, because we already know by now that we have an infinite range. But if we were to then say we could have a mass just outside here, and if that mass is stationary, we could define it to have zero potential energy, right? If it's outside of the mass, outside of this field, this mass here can have zero energy, or zero potential or kinetic energy, zero mechanical energy, if you will. So that means if we want to actually get something to zero energy, if we want a rocket to fire away from a planet to get outside of its reach, we have to put in energy, right? We have to burn fuel, we have to propel that rocket forward, which means we need to do work to get it to be zero energy. So it requires work to reach 0 joules worth of energy. Okay, that means we have to add in something to get up to 0. Therefore, by definition, this has to have started out as being negative. Therefore, must have begun as negative potential. And we'll look at how the value of potential relates to potential energy in the next video. In this video, we need to make sure that we're separating the potential to the potential energy. The only difference is that this is per unit mass. It's not a measure of joules. This potential actually has units of joules per kilogram, okay, because it's the work done per unit mass. And now the second interesting thing about this is that if this is the work done per unit mass, both of these things are scalars. So the potential is a scalar quantity. Now that has some interesting properties. It means that if we were to look at a multi-bodied system, if we were to look at two masses, for example, if we have this as mass 1 and we have this as mass 2, and let's say these are both a distance a, so equidistant away from this point mass here, and a common question for them to ask is, how would you calculate the potential at this point in this field? Now we could draw the field lines for this, and we'll have a look at how the potential is related to field lines. But actually, because this is scalar, when we add vectors, we have to be careful of the direction that they act in. Because this is scalar, it's just a scalar sum. So it just means the potentials sum together. Okay, this is an important point. It means that you can just take the potential due to 1, so you can calculate the potentials one at a time, and then just add them together, one at a time, then sum. Just add the two values, and that's how you get your potential at any point in a field. You can just calculate it from each of them and then add them together. And this is a common question, and this same concept will also apply for electric fields as well. Now, the last thing we need to look at is how do potentials then relate to field lines, and then how can we use those that idea to then relate this back to electric field strength? Because I said they are related. How are they related? So let's first look at field lines. And what we're going to look at is equipotential lines. Equipotential lines. Now, equi meaning equal, potential being potential, which means that actually these are lines where the potential at every point along that line has the same value. Now, I'm going to rewrite this definition out here, or this equation out here, and it means that as long as the center mass is the same and the radius is the same, the potential is the same. Okay, so it means if I have just a single point mass, I can draw the equipotential lines to look something like this. I will have my generic field lines coming out of this point, and then it means that if all of these, I'm going to draw arrows on the very edge, it means that if I were to go a radius r away, every point along that circular line there is an equipotential line. Okay, so this means if you were to move around this line, it takes no energy to do that. Okay, and we'll look at the energy transfer, like I said, in the next video, but it does mean that I can take literally any radius and it will have an equipotential line. So the only way you can change the potential is to move away from or towards this single body. Okay, because otherwise, if you're just moving around it in a circle, you constantly have a fixed potential because you're at a constant radius. Now, what happens if we have multiple bodies? So let's have 2 point masses, and we'll first have to look at the field lines between them. So we're going to have to say, if these are the 2 point masses, we have one field line that's just going to relate them. We have a second field line that does this, third field line that does this. We're going to have another one that I'm going to bring over the top and then under, and then the rest of them are just going to travel out like this. So this is how your field lines look for 2 point masses. And then we're going to say, what do the field lines, or what do the equipotential lines look like in this case? Well, the first thing we can do is say that we know the potential sum. Okay, so we're saying that we need to treat these two as individual sources of potential first, and then we need to say they can only ever be equipotential between the two of them when it's equidistant from the two of them, because it's only based on distance. Okay, so this line here, where we're equidistant from this first mass and the second mass, this is the only position where the potential due to each of them is equal. From there, we have regular things like this, but they're just a little bit skewed. Okay, so they'll be more skewed than usual, just due to the fact that we have this extra potential here. It's going to change it by a slight amount. But if we were to then, like I say, if we were to zoom in, this becomes a single point mass, and then closer to its edge, it will resemble the first diagram a lot more. Okay, and again, this means the only way to change the potential is to move back and forth between these two masses. Now, how quickly the potential changes, we can define, and we call that the potential gradient. Okay, the potential gradient, we're saying if we were to actually move away from this, how quickly would the potential change? And we can draw graphs for this, and we first need to define it as the potential gradient is the change in potential divided by the change in distance. Let me actually write that a little bit closer. So the change in potential divided by the change in distance. Now if we were to graph potential, let me rewrite this equation again. If we were to make a graph of the potential against the distance, notice how I'm only doing negatives because I know the potential on this y-axis can only be negative. It will follow an inverse relationship. This is a reciprocal graph. It's a negative reciprocal graph, which means if we say that this point here, this is the potential from a single body, from a single point mass, we end up saying that this is what it's going to look like. Okay, so you can never get zero potential, okay, but you can also so you can never get zero potential, because to get zero potential R would have to be infinite, and then you can also never get zero radius, or actually when your radius is zero, you'll have an infinite potential. Okay, now why does this relate to gravitational field strength? And that's actually just because if you want to then have some sort of gravitational field strength, it will be related to how easy it is to move forwards and backwards, okay? And that's based on how much energy you have to put in. And actually that means that the gravitational field strength is dV over dr. So this is what I was saying earlier, is the gravitational field strength is the derivative of the potential, okay? And this is entirely true. What that means is I can then go relate the idea of having a potential to having a gravitational field strength by looking at the difference between them. If I then took a gradient at any point here, so if I took this tangent and I calculated the gradient at any point on a potential graph at any point is the field strength. Okay, so now in summary, the important things that we need to know is that G can be written as Gm over R squared. Now G, because we defined it as being force per unit mass, needs to be measured in newtons per kilogram. And then we said that the potential is minus Gm over R, and we said that that needs to be measured in joules per kilogram, and that the gravitational field strength is a vector, and the gravitational potential is a scalar. And this is everything you need to know about gravitational field strength and gravitational potential.